I would like to start with the topic of my thesis, which would be the decentralized operation of the power system. So the problems, or at least some very important problems that should be addressed in this direction are the economic dispatch, demand-side management, voltage control, congestion management, of course, the optimal power flow, OPF. What we want to do here is to formulate them as a resource allocation problem and then try to solve it in a distributed manner or in a decentralized manner. But first I would like to give you a very brief definition, a very basic categorization of the different coordination schemes that could be used in the coordination of the grid. First, it's a fully centralized architecture where all the information is concentrated in one single point. There the information is processed and we have the result of the optimization. A better solution, maybe more efficient, would be to have small aggregations and take more local decisions. And finally, we could have a fully distributed based control where all the peers of the grid are in the same level of coordination, and coordination is actually based on local only communication. So the goal, the idea behind this is to use this type of coordination and actually form a collective task using only local interactions. So why do we need to apply this kind of algorithms? Why do we need these kind of solutions? Simply because we have applications that are larger and larger scale, so we need scalable solutions, and we would prefer to have to avoid the centralized and only centralized coordination, because we would have a centralized point which would be less robust than dispersed intelligence system. So this idea that is gaining more and more interest in the past few years is that we can use this kind of algorithms, these distributed control algorithms, in a way to take decentralized decisions in the grid coordination. So these are also a few very specific advantages of the distributed coordination. As I mentioned before, we have increased robustness of the grid, of the coordination scheme. We have we have reduced communication cost, privacy of the customers, the computation can be performed in parallel, and there is of course tolerance in communication delays, and for me the most important is that this way of designing the system is much more scalable and extensible, and we have plug-and-play capability. So I have written down some of these models that are used in the literature for distributed optimization techniques. The first one, is, which I used also, is population dynamics, but also the very famous are the consensus algorithms and the gossip, which was also used in the DREAM project. We have also synchronized oscillators and two other, distributed gradient and the ADMM. So what we actually did, we'll just say a very few words, and I will present an example of what we did. Let's take the problem of economic dispatch and how we would be able to solve this in a distributed manner. The problem of economic dispatch can be summarized in this objective function, which is the goal is to minimize the total operating cost of the power system, having as a constraint to satisfy the demand plus the losses. So we can take a distributed optimization model, which only uses local information and try to acquire the same solution as a centralized algorithm, but using only local interaction, local exchange of messages. We'll just give you very brief results and stand only in one major conclusion, that from applications of this kind of distributed algorithms in networks with very different size, with different complexity. The first one is this simplified distribution grid with 5 nodes, and the second one is a much larger IEEE test system with 123 nodes. We draw the conclusion that the algorithm takes actually quite the same amount of time to execute. So no matter how much we change, we enlarge the complexity of the problem, these kinds of algorithms manage to respond in a good way.
Good performance, scalability aspects.
Scalability,
yes, very, very good. So,
yeah, sorry.
So, let's see how we have convinced them. So, we have a device, we have a system, we have a first feasibility, technical feasibility, and this is a good candidate to go for industrial deployment.
Yes.
Can we conclude like that?
Yes, I think.
Yes. Yeah. Because this is fundamental for the exploitation.
Yes.
Not research to research. I want research to industry. So this is I think this is a very tangible result, and it's a difficult one. It's a new notion, and this is the concept of coordinated control and distributed control, and bring the device and show the power. I think you need a very big project, bit less than manual, but very important. Thank you, Iasonas. Thank you.